Welcome to our final presentation about openpilot. Driving with openpilot in a way is like taking drugs. It can be chill, but you are never really sure what will happen on your trip. To minimize the risk of a bad trip, we therefore need tests and a prescription. This presentation will take you down the road on how openpilot achieves safe autonomous driving. Consider Bob. He is living in the US and commutes to work every day by car. This takes him over 1 hour, and it is a tedious task. While his car has adaptive cruise control and lane keep assistant, these features work far from perfect. Bob still needs his hands on the wheel to help with curves. Furthermore, he needs to drive manually in city traffic with his foot constantly on the pedal. Unfortunately, Bob cannot afford a Tesla, so he keeps searching for an affordable way to ease his driving. openpilot solves Bob's problem. It utilizes the existing features on the car. Automated lane centering, this makes sure the car stays in the middle of the road. Adaptive cruise control, this facilitates fixing the speed of the car and automatically adopting this if a lead car is slowing down. Lane departure warning, this alerts the user when he is about to leave his lane unintentionally. And finally, forward collision warning. This alerts the user before a forward collision is about to occur. The Comma 2, a $1,000 Android device running openpilot, adds a road monitoring camera to this feature set. It facilitates level 2 autonomous driving. The driver still needs to pay attention but doesn't actively have to control the car. Next, we will have a look how this works under the hood. An important part of the system is the input, which comes from the combination of stock sensors and Comma 2 sensors. The input from the stock sensors gets sent to the CAN bus of the car. Once the data is on the CAN bus, the device called Panda will be able to read this information from the CAN bus via the socket CAN driver. Panda will then send this information to the Comma 2, meaning that the Comma 2 now has all the sensor data available. The Comma 2 uses all the sensor data to produce a plan of the path the car needs to take and converts it into CAN messages. These CAN messages will be sent to the CAN bus of the car through the Panda. Using these messages, the car now knows if it needs to change its speed or steering angle. We will now take a look at how the Comma 2 produces the path plan of the car. We will discuss two scenarios to explain the creation of the path plan. The first scenario is that the lead car brakes or slows down. In this case, board D will receive the messages from the Panda and publishes these messages. Radar D is listening and will combine the radar CAN message with the data published by Model D and publishes a radar state message. This radar state message is picked up by Planner D, which creates a planning of the path the car needs to take and publishes this plan. Finally, Controls D converts this path published by Planner D into CAN messages in a car-agnostic way and sends it back to Board D, which then writes them to the car's CAN bus via the Panda. The second scenario is a road curve. For this case, Camera D has the responsibility of publishing video frames from the back and front facing cameras. Model D transforms these frames using its machine learning model and publishes the result. Planner D will use Model D's output and incorporate it into the path planning. The updated plan, containing the steering wheel torque change, will be converted into CAN messages by Controls D, which Board D then writes to the car's CAN bus through the Panda. To get a better understanding of how the communication between the processes in the Comma 2 works, we will now discuss this in more detail. So, are we able to recognize familiar design patterns if we look into the code? The most notable one is publish and subscribe, which is also known as PubSub. Briefly said, publish and subscribe is a system to orchestrate message passing between different software components. The publishers only send, while the subscriber solely receives messages from the publishers that it is subscribed to. Please note that a specific software module can be a publisher, a subscriber, or both. You can think of this like an address book. Each module has a list of other components with an address. Let's go over an example by looking at the previous figure. The arrows represent messages that are passed by openpilot's own message passing system, Serial. The central mouthpiece is the bus. It orchestrates different messages between the different modules. This pattern plays a fundamental role in the autonomous driving system and contributes to multiple factors. One, it ensures extensibility because it keeps a system modular. And two, it makes the system universal, since people from the open source community may already be familiar with this architectural pattern. PubSub is particularly useful when an application asynchronously communicates with other applications that are not necessarily implemented in the same language, or even executed on the same platform. Within each component, it allows for cherry picking from the available publishers. This ensures that critical information only resides in the places where it is of vital importance and introduces extensibility. So how do you test a driving agent without involving physical cars? As we've learned, openpilot uses a message queue for communication between processes. Unit tests in openpilot leverage those queues for black box testing. Components are often tested by sending messages to them and running assertions against the messages that are published in response. This is different from the traditional unit testing scenario, where a unit is often a function or class. In this case, a unit is a process. Besides unit testing, openpilot's continuous integration process also uses a lot of integration testing. For example, it simulates predefined maneuvers and verifies whether openpilot does the right thing in the given situation. Each of the 23 maneuvers take about 15 seconds to run, adding up to around 5 minutes in total. When refactoring code, it is often very helpful to know whether you've made any unintended changes to the system's output. To combat accidental changes in openpilot's output, the developers built a repository of pre-recorded drives and the expected output. The recorded drives are then replayed by the test script, comparing openpilot's output against the reference output. Whenever the output of openpilot changes, either accidentally or purposefully, the changes will have to be reviewed by the developer, who can then choose to update the reference data when the change is intentional, or fix their code. The command to try to identify the car it is connected to and engine startup. The series of messages produced on the canvas at start is assumed to uniquely identify a car. This series is then matched against a collection of known series called fingerprints. When openpilot successfully matches against a known fingerprint, it can apply the correct decoding specification to interpret the CAN messages. Later, when sending control messages to the actuators, car-specific parameters can then be taken into account. The goal of openpilot is to constantly improve the driving quality and safety. To achieve this, the machine learning model and other code to compute adjustments is on a frequent change. To avoid maintenance of such a model for every single specific car, a general car state object is used to act upon instead. These car state objects are created by a car-specific carstate.py function from car-specific CAN messages. Carstate.py uses a car-specific .dbc file containing the CAN message encoding and decoding scheme. It furthermore uses the common type specification of a car state object created in car.capmp. The adjustments computed by the model, called from controls.d.py, are returned as car controller objects. These objects are then consumed within a car-specific carcontroller.py script. This script in turn creates the car-specific messages for autonomous driving.